All right, this is the 14.1 and 2 notes for stat honors. We're going to be starting our studies of regression and bivariate data. Basically, in the beginning here, we're going to go through a little bit of a review of algebra and linear equations. We're not going to spend a whole lot of time there, but part of all of this concept is, what if you have two data sets that you need to make some comparison between to find if there's some relationship between the two data sets. So we're going to start with just an algebra review just to make sure everything is good with that. So just remember, going back to algebra, the slope-intercept formula line, most students remember it as y equals mx plus b. It's going to be a little bit of a change just because in statistics they use a different variation of the formula. So this is actually what it's going to look like. So it's going to be y is equal to b sub 0 plus b sub 1 times x. We are going to be using, so you can see the m, which is next to the x, has now become b1. So this is the slope, basically. So you can see b1 represents the slope. And the b0, which is at the end, now is rotated to the front. And which, because obviously you can do that, obviously commutative property allows you to either order you want with the plus sign. But that now is in the front as b sub 0. So b sub 0 is called the y-intercept. Okay, so in this scenario, basically what we're looking at is the same exact formula. It's just that there's just a different take on it, right? So you just want to get your brain sort of set up with making sure that this formula is good. Now, a couple things. The y-intercept and slope have a definition, which are actually going to come in handy with some of the problems we do. So the y-intercept is defined as the value of y when x is 0. So it kind of makes sense, because if we made this 0, it would wipe this out, and it would give us the value of y, right? So that is something we want to take note of, because if we were to do some type of, linear equation based in business or money, financial, you want to know what the business started with in terms of money, things like that, then this is obviously something that's important. Now, the really important definition is slope, and you will be asked this for sure in various parts of the lesson and in labs, blah, 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 homework. So what is the slope? It's the amount of increase in y for every 1 unit increase in x. Okay, that is something that you want to somewhat memorize, make sure you know, because you will be asked for that if they ever say to interpret the slope. So you would immediately say what the increase in whatever the y variable is based on 1 unit increase in whatever the x variable is. Just a note from earlier things, so the y variable is usually called the response variable. The x is usually called the explanatory or predictor variable. Basically, I always remember y is the response, because this is what you're actually going to be calculating most of the time. That is going to be the response of whatever you put in for x, essentially. So just a reminder about linear equations and how they work, and also the fact that we now have a new take on that equation with variables that are a little bit different. Let me read here. It says, note that linear equations can have slopes that are positive, negative, 0, or undefined. Since best fit lines are of the form y equals b naught plus b1x, we only deal with non-vertical lines. Okay, so what does that mean exactly? So vertical lines have the equation x is equal to a number. So obviously, that does not fit this form right here, which means we immediately eliminate vertical lines as a possible best fit line. Whereas when we're talking about all the other types of lines, for example, a rising line has a slope larger than 0, right? Rising line. We have a diving line or falling line, which means the slope is negative. But if we have a slope of 0, we get a horizontal line. So just note on that. in this scenario that's something that these are what the best fins would look like. And by the way, you're not going to get a lot of these as best fit lines either. They're mostly going to be rising and falling lines with positive and negative slopes. Okay, so just reading right here. It says, when it comes to real-life applications, one must understand that it is rare that one variable can exactly predict another to achieve a perfect linear relationship. Rather, we must often rely on rough predictions that fit a line to a set of data. Okay, so what does that mean exactly? So it's as rare as possible to get some relationship that have 5, 4, whatever points that all fit on a perfect line. Like, this is in the randomness of the world, it is very difficult, almost impossible to achieve something like that. So essentially that is your introduction to regression, which is the study of best fit lines. So fit being the key word there. So let's look at an example here where we have 3 data points that I listed, x, y coordinates that are going on here. And our goal, overall goal in the next pages, is to determine a linear equation that best fits these 3 points. So just so you know, whenever we have 3 points and we want to graph it, we call it a scatter plot. So generally, or more technically, when we want to graph bivariate quantitative data, we use a scatter plot. So let's plot that data. We have 1, 3, we have 2, 1, and we have 3, 5. So the key now in terms of finding this best fit line is determining what would be the line that would best fit the 3 points that we have on this graph. So would it be this line? Would it be this line? Would it be something in the middle? We don't know yet. So the goal is how do we do that? Well, there's a statistical method for doing so called the least squares criterion. And it's basically defined as follows. This least squares criterion creates a line that best fits a set of data points, which will create the smallest possible sum of squared errors. So basically, this statement right here, smallest possible sum of squared errors, which you don't know anything about yet, is what we're going to be hammering home for the remaining, like the rest, not all of the section, but a lot of the section. We're going to be talking about how to generate this smallest possible sum of squared errors to create this perfect line. So moving on. Okay, so how exactly does this least criterion work? All right, so what I did was I have these 3 points that we graphed that I have in green here, the points. And I have generated 2 examples of possible best fit lines and their equations. So the first graph, we see that there is a line here going up from here to here, right? That line is a best fit line that happens to travel through one of the points, and it looks like almost halfway through the other 2. This equation is y equals -1 plus 2x. Now note, whenever we talk about regression lines, we always use the variable y hat to determine a best fit line. So just take a note of that. In terms of if you've seen the hat designation before, but it's similar for this. I also generated another line that doesn't go through any of the points over on this side, right? Doesn't go through any of the points, but the same 3 points are there. This equation is y equals 1 plus x. So both of these clearly are in the form that we talked about. So remember, y hat equals b sub 0, our y-intercept, plus b sub 1, our slope, times x. They're in that form. So the question is which one's better? Well, we'll talk about that in a second. We want to talk about some important sort of terminology. So in terms of regression first. So it says, why exactly would we use y hat as the variable why don't we just use the variable y, Why? Why do we have to use y hat? Well, if you look at this graph, there's actually 2 values of y happening on the graph itself. I know that sounds kind of weird, but there is. So just for example, look at the first graph at x is equal to 1, which is right here. If you look up on the possible values of y, you can see the coordinate y, which is right here, for the coordinate. But isn't there a value of y also on the regression / best fit line? So the key is understanding that this value here, which is the point, is called the actual y, actual. And it's at y, and it's y equals 1. But we also have the predicted y, which is going to be, this is 3 by the way, not 1, which is going to be y hat is equal to 1. So in these scenarios, every single time you have a value of x that has a coordinate associated with it, you are going to have two values of y. You're going to have one that's the actual coordinate y, and then you're going to have one that's the predicted value of y, which is on the best fit line. So this creates a very important scenario, and this is the case for all of them. Just like if you went to x is equal to 2 right here, then you have a actual y of 1, but then you have a predicted y of 3, which is backwards from the original one, worth noting. So you basically have a different y for each one, which is what I explain right here for you, if you want to look through it just from that point. So you want to get used to using the proper y for every scenario that you have in any problem that you work with. So this is obviously going to be pretty important with what you're going to be doing. Okay, so just returning to our regression stuff, which we're going to start here. It says, returning to our overall scenario, what makes the line the best fit is, again, the smallest possible sum of squared errors. In general, the error E is the vertical distance from the line to the data point for each data point. Okay, so just to be clear, if we go back to this example right here, so you notice we have the actual y and the predicted y. Well, this distance right here is the error. So the vertical distance from here to here is going to be the error in this scenario. And you can clearly see that there's a distance of 2 going on there. So if we go to the same scenario, here it is right here, right? So there is a distance of 2. Now note, there's a small thing we have to take note of here when we're doing it. So it says, the following diagram shows the error computations for each point, which is essentially the calculation y minus y hat. So that is important because you always have to take the actual minus the predicted. So if you're looking at this scenario, the actual is 3, the predicted is 1, so 3 minus 1 will give you 2. But if you go to this scenario over here, the actual y is the coordinate at x equals 2, is y equals 1, but the predicted is y hat equals 3, which means when you do 1 minus 3, you get negative 2. Of course, if you look at the last point in this scenario, at x equals 3, note that the y and the y hat are the same value because the point is on the line, which means if you subtract them, you get e is equal to 0. So if you're looking at this problem right now, we actually have 3 computed errors in the scenario. We have 2, -2, and 0 for our 3 points. There is an error computation for each point that you have. Just like if you go over to the next line right here, we can look at this and go, all right, well, look at our first value of x, which is 1. Our actual y is 3. Our predicted y, which is on the line, is 2. So actual minus predicted, 3 minus 2, gives you e equals 1. You can see that hopefully what you're kind of understanding or seeing from this is if the point is above the line, then the error is positive. If the point is below the line, then the error is negative. And if the point is on the line, then we're going to clearly get an error of 0. So these error calculations, believe it or not, are what tell us the better best fit line between these two graphs right here. So that's what we're going to do in the next part here, is we're going to do some calculations to show that. All right, so it says, therefore, if we find the square of each error value, e squared, and then take the sum for each best fit equation, the sum of all the e squareds, we will get the following. Okay, so if you go over here, I created a nice little table that'll work pretty well. So if you look at this, we have x and y for each one of these. I also put a predicted y on here. So for the first graph, we can go through and look at our y's are at y equals 3, y equals 1, and y equals 5, right? But what about the predicted y's? So those are here, here, and here. So the predicted y's are going to, at 1, 2, and 3, these 1, 2, and 3, are going to be 1, 3, and 5, which is what we're going to put in right here. 1, 3, and 5. Okay, so basically what we're going to do is we're going to do the same thing for all of the error calculations. That's going to be basically where we're going with this. So let's go to the other line. So all the y's we had, just to verify, are at y equals 3, y equals 1, and 5. So those are our actual y's. But our predicteds are at 2, 3, and it looks like 4 for the y hats. So 2, 3, and 4. Okay, that's not coming up well, but I'll change the color. So what do we need to do for the error? So error calculations are y minus y hat. So those are actually all the numbers that are on, these here. But let's just say we were using the diagram. We would do 3 minus 1, which is going to give us 2, which is our first value over here, 2. And then we would do negative 2 and 0. If we subtract them over here, we do 3 minus 2 is 1. 1 minus 3 is negative 2. 5 minus 4 is 1. So remember, we want the sum of the squared errors. The sum of the... So right now we have the non-squared errors. So if we square them, we get 4, 4, and 0. We get 1, 4, and 1. If we take their sum, we get 8 and 6. So what is the proper regression line or best fit line to use? It's the one with the least squares criterion, or in other words, the lowest possible sum of square errors. That would be, ta-da, this one. So therefore, we know that of these two equations, y equals 1 plus x is the proper best fit equation to use for this scenario. So this equation is basically the proper least squares equation to use. And of course I just did a mini definition of this. So basically we define a regression line as the line that best fits according to the least squares criterion. So we use basically least squares criterion is the main requirement that we have. So we just by default call it the perfect regression line, or the most ideal one. And then any regression equation is the equation of such line, which of course is y equals 1 plus x, but more formally y hat equals 1 plus x, now that it's a proper regression equation. So if you look at just what we just did for this entire scenario, we had two equations, but a lot of students will say, like, where did you come up with these equations exactly? So why did you choose these equations right here as the ones to use? Well, to be honest with you, I actually did the calculations. So I went and did the calculations for the least squares, and these two were the two best fitting lines in terms of a least squares criterion. So I used them as an example. So where did those lines actually come from, though? So how do you actually calculate a regression equation from scratch? Well, just like a lot of the things that you're going to be doing in this section, the statistics is quite involved. And that's sort of an understatement. It's similar. It's not super similar to when we did ANOVA, but it's a little bit easier. But it's the same idea. We have to go through tables to figure out some of these things. In reality, you are going to be using the calculator a lot to produce these regression equations, but you need to know where they actually came from. So the little squirrels running around in your calculator when you say calculate a regression, what are they actually doing? What's the code that's in there that's actually in the formulas that are creating this? Well, that is essentially this box right here. So if we are, again, going by the fact that our regression equation is y hat is equal to b sub 0 plus b sub 1 x, then we define the slope as the following. S sub xy divided by S sub xx, and we define the y-intercept as one of two different equations, either y bar minus b1x bar, or 1 over n times the summation of y, sum of y, minus the slope times the sum of the x's. So note, in either scenario, in order to calculate the y-intercept, you need the slope. So it's obviously you have to calculate the slope first, or you're not going to get anywhere with this. But just realize that there are two equations that we could use. When we do practice for this, I'm going to be doing both of them because I want you to be able to do that. Now, another small thing that's of importance is you also have two variables, several variables in here you might not be familiar with, but we're going to concentrate on these guys. So SXY and SXX. So SXX and SXY don't really have a name per se for them. I've seen different things over the years from different books while they'll attempt to name them. They're usually actually named by their formula. So the defining formulas for these guys are over here, specifically the first two. These formulas should be familiar to you because they're very standard deviation-esque in the sense that here you're taking all the individual x's and subtracting the mean of x bar, and then squaring them, taking the sum, and then this is going to be the sum of all the x minus x bars and y minus y bars. So obviously we're going to use a table for that, which is going to be down here, by the way, in order to calculate those. But essentially what we have is we're going to go back to this scenario of this regression equation where we had these points right here. And we're going to derive this equation, which we found to be our regression equation, by using the computations that are going on in this gray box right here. That's our goal. So if you look at the 3 points that we have here, we first, in order to do anything, you notice that this equation here has y bar and x bar, so we need to find those. So let's look at our x column here. So what is the average of 1, 2, and 3? Well, we could add them up, let's say, and get 6 and divide by 3 to get 2, but clearly 2 is going to be the average of 1, 2, and 3. Y bar, what is the average of 1, 3, and 5? Clearly that'll be 3, but if you want to add them up and get 9 and divide by 3, you're going to get 3. So that's going to help us right off the bat. So what do we need to do basically? Well, if we want to calculate the slope, we need this SXY and SXX formulas, which are here. So in order to do that, we need to use the table. So remember, x bar is 2 and y bar is 3. So for this column right here, we need to take every x value and subtract 2. So we're going to get -1, 0, and 1 as our values. We then go to our next column and go, now we have to take every y value and subtract 3. So we're going to get 0, -2, and 2 as our values. So far, so good, right? Now this column is going to be taking this column and squaring it. So we're going to get 1, 0, and 1. And then this column here is going to be taking the product of these two columns. So we're going to take -1 times 0, which is 0, 0 times -2, which is 0, and 1 and 2 makes 2 with multiplication. So hopefully you followed that. Basically, Once again, this column is take every x, subtract the mean. This column, take every y and subtract its mean. This column is squaring the x minus x bar column. This column here is taking these two columns and multiplying them. So if you just look right now at these defining formulas over here, SXX is simply the sum of this column right here, which means that's 2. XXY is the sum of this column here, which is again 2. So we should be able to take these over here and get 2 over 2, which is 1. So the slope of this line is officially 1. Once we get that slope, we can then, let's say we decide to use the first formula for slope. All we have to do is do y bar minus b1 times x bar. Well, y bar is 3. We subtract b1, which is 1 right here, times x bar, which is 2. If we do that, we get 3 minus 2, which is 1. So if we now take b1 and b0 and plug it into the regression equation, that is incorrect, we would get 1 plus 1 times x, which is 1 plus x. So the regression equation is y hat equals 1 plus x, right? If we go back officially in our colored thing right here, that is exactly the equation that we got when we determined that had the least sum of squares. So that is how you calculate a regression equation from scratch. So ideally, we probably want to run through another problem and do the whole thing out. Number 1, it says the following displays the age in years and the price in hundreds of dollars for a certain car. All right, so if you look at the data, which is right here, so we have, let's say, a 5-year-old car, which is going to be $8,500. We have a 4-year-old car, which is going to be $10,300. So just to give you an idea of what the data looks like. So what we're going to do is we're going to use the calculator. So you want to get your graphing calculator out, just like we've done many times before in class, and you want to put all of the age data in L1 and all of the price data in L2. So if you want to just pause and do that, you can. Now, what I did was I included a scatter plot of the data that's sitting right here. So the scatter plot, you can clearly see, has age on the x-axis, which is going to be our predictor variable, and price on the y-axis, which is going to be the response. Hopefully this makes sense to you because we're using the age to predict the price. The price is going to be whatever you're going to get as a result of the age. So that's how we set up the x and y axis. If you look at the points, we clearly have a decreasing relationship, which we'll talk a little bit about later. But of course, that's obvious because the age, as the car gets older, the price of it is going to go down. Okay, so what about graphing this with your calculator? So we don't need to do that, obviously, because we have the graph right here. But in most problems, you're going to want to graph it. So let's talk about that. So just remember, you're going to your stat plots. We've done that many times in our class. So that's second y equals. And in stat plots, you want to go to the first one and make sure it's on. If you go in there, you're going to see type. So you're going to choose the first one. The first one is basically something that looks like this, right? So that's the one you're highlighting. Then that should open up two options for the lists, X list and Y list. So for those lists, you're going to put L1 and L2. Remember, L1 and L2 are actually located above the 1 and 2 keys if you hit the blue second key. From there, everything else you can leave the same. The key is that you want to go to the zoom menu, which is the top middle button on your calculator, and then just click 9. Sometimes, as I've stated in class, you do have to quit in this step right here in order to get zoom 9 to work. It just depends on the software on your calculator, but that will result in the regression equation you have right here, or the scatter plot you have right here on your calculator. Okay, so what's next? We want to do the regression equation. You want to compute it, just like we did in this problem, but what's the difference? Well, here we had 3 points, now we have 11, so doing this can be quite involved. And truthfully, you probably won't do much of this again, but I want to show you how the lists on the calculator can be very useful. Before we do that, of course, though, we do need to know the mean and the means of x and y. How can we do that? We can use two var stats, L1, L2, which will give us those means. Those means are going to be 5.27 and 88.64. Okay, so ideally what we want to do, instead of doing all these calculations by hand, we want to use the list. So how do we do that? Well, first of all, we already have these sitting in L1 and L2. So now what we want to do is we want to take all our x values and we want to subtract 5.27. So how do we do that? We take our cursor and we move it all the way to the top and highlight L3, press enter on L3, and then the cursor will appear next to it. In there, you just want to type your x, which is our L1, that's our x column, minus 5.27. Once you press enter, then all the numbers will populate the table below it. So you're going to get negative 0.27, negative 1.27, and so forth. I'm going to pause and write them in a second. So what you're going to do for the next column is we're going to go to L4, highlight it all the way at the top. You'll see the blinking cursor next to it. And this time you're going to take all your y's, which are stored in L2, and you're going to subtract 88.64, which is our y bar. And you will end up with negative 3.64, 14.36, and then I'll be back in 1 second. Okay, so instead of wasting your time, I filled in all of these numbers, which you already have on your calculator, so you can sort of glance at them, that they will all be set up this way. So far you have your L1 through L4s stacked up. So what about L5? We need to now take L3 and square it. So go up to your L5, highlight it, have the blinking cursor, and this time you're going to do quantity L3 squared. So what will happen when you do that? You'll end up with 0.729, and I'll be back again. All right, and there you go. All the numbers are there for you, so you can verify those. Everything's working instantaneously right now for you in your calculator. So the last column, we go to L6, we highlight it, blinking cursor. This time we need to take the columns L3 and L4 and multiply them. So you're going to do L3 times L4, and you are going to get, again, 9828. I'll be back. All right, and there you go. So those are your numbers. These numbers I've checked over the years, so they all should be good. But basically, you get all the values of importance for what we're going to use this table. So this table is equivalent to the one here that we did by hand, but the numbers were much easier. I can't imagine going through this manually, and you probably wouldn't have to do that in most circumstances. This is just a good example to go through. So let's, what was the point of all this? So remember, the first thing we always have to calculate is B1, the slope. B1 is equal to SXXY, SXX, right? So if you recall from our problem that are defining formulas, so our SXX is the sum of our x minus x bar squareds. So that is our L5 column. So the sum of this column is 20.1819. Okay, so you can actually get that value by using the calculator as well. Okay, so if you go on your calculator to, if you usually go stat edit, so if you look above stat, you'll see a list. You want to go to that. So you'll hit second and the stat button to go to list, and you'll go over to math. If you go over to math, you're going to see number 5 is sum. So you want to do that like on the main screen when you quit out, and then you can just type in sum of L5, and you're going to get the number that's at the bottom there, 20.1819. So similarly, if again you go to second stat and go to the list command, go over to math, and do the sum of L6, that's going to give you the value down here, which is actually SXY, which is negative 408.9092. And just to be clear, for some reason you have really difficult time following. I know some people have a tough time following calculator directions. it is what it is. All you have to do is go into Google and just type in sum on 280 TI-84, and it'll give you a video on how to do it. Remember, in Canvas, I put a ton of videos on how to do a lot of these things, so use that as well. So if we have these two values, we can now put them in over here as our numbers of importance, which means we're going to get approximately negative 20.26 as our slope for our regression line. So next we need to calculate b sub 0. Now, last time I used this formula, which is the first one that's going on right here. So since it doesn't matter, I might as well use this formula now, just so that you get experience with it, and you are, you can be flexible in going either way when actually calculating it. So I'm just going to rewrite that formula down here. So it's going to be 1 over n times the sum of y minus the slope times the sum of x. All right. So if we actually use that formula, we're going to get 1 over 11, because there's 11 cars, right? And we're going to do the sum of y, well, we calculated that to be 975, minus the slope, which is negative 20.26, times the sum of x's, which is 58. If we do that, we're going to get 195.47 as the y-intercept, which means we can then say that our regression equation is going to be 195.47 minus 20.26x. Okay, so it's definitely, it is what it is. You can mathematically go wrong anywhere and create this. Also, by the way, these means were rounded to 2 decimal places. It wasn't a huge deal because you're not going to be doing this a lot. You're going to be using the calculator too, but that also would create a little bit of error here, but not a big deal. This is generic, just so that you understand how to find a regression equation. This is how you do it, and this is a good example of said problem. Okay, so let's answer a few more questions when it comes to this regression equation. So what I did was I took this equation here and I plotted it on the original scatter plot here. Okay, so you can get a view of what the regression equation looks like superimposed on the scatter plot. So it looks like it's pretty realistic. The line is going through the points pretty accurately, and it gives you, and according to our calculations, this fits the least squares criterion. It produces the least sum of squared errors. Did we calculate those sum of squared errors? No, but we didn't need to, because these formulas that we use in order to calculate the equation, it has that built into it. So we now know that this is our least squares equation. So our first question is, how would we describe the very logical relationship between age and the price of car? Well, we talked about that before. Basically, as our x variable age increases, then our y variable price decreases. Okay, we know this logically anyway, but it's important to see the linear relationships and what they mean. Whenever you describe a relationship like this, you always talk about what you're doing with x, either increasing or decreasing it, and then the result is y, because again, this is the predictor variable and this over here is the response. So you always state it this way. Okay, what about this one? I warned you about this one. It says, correctly interpret the slope of the regression line in terms of the prices for this car. So we defined slope, I'm not going to go back, but we defined slope a while back as essentially the change in y per every increase, one increase in x, 1 unit increase in x. So we're going to do that. So I'm going to write it out as a blanket statement. So this is what you wouldn't write for this problem, but I'm going to write it just as almost like a formula. It's the change in y per every 1 unit change in x. Okay, that is the formula for doing so. So how would we say that? Well, What is y in our problem? Price per 100. What is age? It's year. So how do we write that? So this is going to be, if we look at our formula right here, this is our slope. Our slope is negative 20.26, right? So this implies, because it's negative, that we are losing money. So a car loses, so again, change in y would be loses 20.26. But remember, this is in hundreds. So that means we are losing $2,026 in value per every 1 year. Okay, so again, it's the change in y per every 1 unit change in x. That is how you would exactly, and there's no, students often get very wordy with this. This is exactly how you interpret this, so make sure that you do it, write it just like this. This is the best way to interpret the slope. Also take note that they didn't ask you to interpret the y-intercept because basically it's probably because it's not going to be very accurate when it comes to this line. We'll talk about that a little bit later though. Okay, last one here for D. It says use the regression equation to predict the price of a 3-year-old and a 11-year-old car. Okay, so you guys should be experts at this. So what is age in this problem? What variable? It is x, right? X. So all we're doing is saying for x equals 3, what is the price going to be? Well, all we do is sub it into our regression equation. So we would do y hat, which is our predicted y, is equal to 195.44 minus 20.26 times x, which is 3. We would get approximately 134.69. This in hundreds means we're going to get a price of 13,469. For x is equal to 11, we would do the same thing. We would take the same regression equation. Remember this one. This is a 7, by the way, not a 4. 195.47. Right? We would do minus 20.26 times 11. And we're going to get approximately negative 27.39. Okay, so this is an interesting one, right? Very interesting one. And if we interpret that, we're basically going to get negative $2,739. Okay, so this is going to be relevant in what we talk about next. This is clearly something going on wrong here, because we're not talking about, you can't have a negative price of a car. Okay, so just furthermore, when it comes to that, it says I'm going to read. The abnormal predicted price of the 11-year-old car in D brings up an important concept. It is very likely that the regression equation was only meant to be accurate for certain age ranges, let's say from 2 to 7-year-old cars. Okay, so let's take a look at that. Let me get rid of the writing on here. So from 2 to 7. Okay, so what they're saying is that this line might only be accurate from here to here. And that makes sense, by the way, because when you get outside of that, maybe the equation isn't very wide. And we don't have a lot of cars that are greater than 7 years old in the terms. A lot of people buy new cars pretty fast. So going on, it says, therefore, when we utilized it to predict the outside the range of values it was meant to, the linear relationship we mapped out didn't hold anymore. Generally, one must take great care in only utilizing a regression equation for prediction within the observed values of the predicted variable. So any prediction outside the range of values could lead to a concept called extrapolation, which often results in grossly inaccurate predictions. So what it's saying is this was only meant to predict here. So if you start predicting values outside of those ranges, you are going to end up with answers that are not accurate. Now note, a lot of regression equations come with that information. they state only to use it on a certain standpoint. So worth noting that that is the case when it comes to a lot of these regression equations. Okay, before we move on, let's talk about more calculator work. So you'll notice here that, we found this regression equation and we were able to superimpose it on our scatter plot that we created. So how do we do that on the calculator? That's the next step. So in terms of calculating this equation, so in your calculator, you will find the same place where 1 var stats and 2 var stats is shown. You want to hit stat and then go over to calculate. If you go over to down to number 8, you will see linreg a plus bx. Now there's another one, number 4. Don't use that one. It'll be confusing. Instead, use linreg a plus bx in order to calculate it. So when you do that and you open it up, what you're going to find in that menu is the only thing of importance. There's 3 things of importance. There's obviously your X list. Okay, now according to what you have in your calculator right now, that is L1. Your Y list is, of course, L2. And then you also want to go down, leave frequency blank, by the way, frequency list, freq list. You want to go to where it says store reg EQ, that's a double E, EQ, and you want to put the variable Y1. Okay, so where do you find that? We've done this before, I believe. You're going to go over to vars on your calculator, the vars button. You're going to go to Y vars. If we haven't done this, then don't quote me on that. We might have not. And we want to go to function. Okay, this will get you to Y1, which you want to click. Now, why is Y1 important? Because it's going to take your equation and put it literally in the Y equals menu. So why is that important? Because that's what's going to get your line on top of your graph. So if you hit enter after doing all of this, what's going to come up is basically a summary of, hold on one second, quit. What's going to come up is a summary of your linreg. So what's really cool is you should see y equals a plus bx, and you should see a is equal to 195.46 something, 8 I think, and then b is equal to negative 20. So obviously the variables are different. That is annoying, but you just got to get used to it. And clearly that is your equation right there. If you look at the equation we calculated, we actually get the same thing. Now, one small thing though, actually we'll talk about that later. For now, we'll just deal with what we have now. We have our equation, we have what it is. So now what I want you to do is quickly just hit, again, zoom and then 9. So zoom and 9 and watch the graph. What you'll see is this on your graph. You'll have the equation going through it. And why is that? If you click the y equals button, you're going to see the exact equation of your regression stored in y1, which is why, so right now your stat plot and your y equals is running at the same time on top of each other, which is creating this wonderful depiction of your regression model on top of things. So it's actually quite nice, and you can use that to your advantage when doing this graphing. One other thing, this down here. So let's just say you didn't want to round these numbers right here. You can actually do this quite easily on your calculator as well. If you quit out and just go to your main screen, I'm going to do, let's do this one. So right now you have your equation, this equation, right, with an x in your y1. So if you go back to where the y's are located and hit variables, y variables, and function, and hit y1 on the screen, if you do a parenthesis and then take the 3 and put it in it and press enter, what that is function evaluation. It's saying take 3 and put it into y. If you do that for your problem, you are going to get a more accurate version of 134.69. It could be exactly that. We might not have that much error in our problem because we did all this using the calculator in the table, but you're going to get the most accurate evaluation of that equation. So I'm just trying to give you as many shortcuts as possible using the calculator so that you can verify your work, but that is another way to do it. Also remember, all of this should be in the videos I posted on Canvas, not this video, but I posted videos that are related to the calculator in the calculator module. So you can also read through this if you're not sure or following what I'm doing with this in terms of using the calculator. Okay, just a couple more things to cover. At the top here it says, just to add, it turns out in this example that prediction in the following areas leads to extrapolation of car prices. So remember, we just talked about how if we predicted this outside 2 and 7, then we might lead to extrapolated results. Well, it turns out that that is exactly the case. So look at the dashed part of the line. It turns out everything before 2 and after 7 in terms of x values turns to an extrapolation. So we want to be very careful with that. But there's more to that than you would think. So let's talk about that. It says you might have noticed that we have one data point, namely 2, 169. So again, 2, 169 is right here. Okay, this data point is a bit away from the other data points. So the other data points are like scrunched here, but then you have your 2, 169 over here. So what is that all about? So let's take a peek. So it says, hopefully this should remind you of the concept of outliers, which once again could occur with bivariate data. So we don't know if that's an outlier yet, but we want to investigate that because it is away from the other points. It says an outlier is an observation that lies outside the overall pattern of data. In the context of regression, an outlier is a point that lies far from the regression line relative to the other data points. Okay, so my question is this point farther away from the regression line than these points? Hopefully what you say is absolutely not. So even though this point is far away from the other points, generally if you look here, the distance between this point and the line is very similar to the distance between these points and the line, which means, believe it or not, this is not an outlier in this problem. So yes, that is a little confusing for students in the beginning, but remember, outliers in regression are going to be defined a different way. They are not a point away from the other points, but a point away from the line. Okay, continuing on. It says we must also watch for something called influential observations. In regression, an influential observation is a data point whose removal causes the regression line to change considerably. Usually, a data point separated in the x direction from the other data points is often influential because the regression line will be pulled towards such a point. Okay, returning to 2, 169, which is now on this graph. If we remove, this is, by the way, this is the original regression line right here, this one, okay, if you recall. And all the points are the same as what we've seen before. So that's our original regression line. But if we remove this regression, this point, 2, 169, and did the regression again with only 10 points, we would get this line right here, this orange line. And this would be the new equation. So this line is actually drastically changed by the removal of this point, which is very much different in the x direction from the other points. Therefore, we would say that even though it's not an outlier, it is an influential observation for our regression. So to be clear, we can visualize an outlier from a graph. by just looking at how far it is away from the regression line. But an influential observation must be computed by its removal and how it affects the look and equation of the regression line. We don't really have a standard for that. We more just look at how the line changes. So what this does is this creates a very interesting situation, which I'm going to read here. It says, please note that an outlier may or may not be influential, whereas an influential observation may or may not be an outlier. Could it be both? Absolutely. Could it be neither? Absolutely. But the key is that one does not necessarily correlate to the other or have a relationship to the other. One could be one and not the other. That is an important concept that's going on here, so you want to make sure that you are clear on that. Okay, and finally, be very careful. So when we talk about regression in this textbook, for your purposes of learning about best fit lines, we are talking about linear regression. If you look in your menu where you did linreg, there's a bunch of other regs. So there's sine reg, there's quad regs, there's a bunch of other regs. So we are only talking about linear regression. So realize if you put a bunch of data into L1 and L2 and perform a linreg, the calculator has no idea what the data actually looks like. So let's say you put these data points in the L1 and L2 of your calculator. It will produce a regression line that looks like this. Okay, but as a human being, as a person with eyes, you have to understand that you must always create a scatter plot first to make sure that your points are actually in a linear relationship. Clearly, that this is a curvature of a relationship, which means a linear regression would not be a good use for our scenario. So, really the summary of the story is all these formulas that we use, they don't have eyes. I know that sounds corny, but they don't. They can't see. Only the user, the statistician, the student, whoever, they can see by graphing the regression line, or graphing the scatter plot of the points, making sure that it actually appears to be in a linear type pattern that could fit a linear pattern. Once you do that, then you perform a linear regression. If it doesn't fit the pattern, it has some type of curvature or crazy pattern, then you shouldn't be doing a linear regression for it. So this is pretty much a big deal, obviously. I do it at the end because I just want to make sure that students are all about that and being observant about using those scatter plots.